Hey everybody, so we have finally made it to Python object-oriented programming. This is a very important topic. In Python, an object is a bundle of related attributes and methods. Attributes are similar to variables to describe what the object has. So look around you right now. You are surrounded by different real-world objects. Next to me I have a phone, a cup, and a book. Each of these objects can have different attributes to represent it. For example, an attribute of the phone next to me could be version number. I could set that to be 13. Is on could be another attribute. Is the phone powered on or not? That could be true or false, or even a price. I have a cup next to me. What liquid is within the cup? In this case, coffee. What's the temperature of the cup? Is the cup empty? Is empty. Or even a book. What's the title of the book? That could be a string. How many pages does the book have? Pages could be another attribute. Now, objects also have the capability to do things. They have methods, which are functions that belong to an object. People mix up functions and methods all the time. They're technically different. Even when teaching, I tend to make that mistake, calling a method a function and a function a method. Usually people know what you're referring to, though. A method is a function that belongs within an object. What are some actions these objects can perform? With a phone, you can make a call or receive a call, turn the phone on or turn the phone off. Those could all be functions. With a cup, you could fill the cup, drink from the cup, or empty the cup. With a book, you can open the book, read the book, and close the book. An object is a bundle of related attributes and methods. They can represent real-world items. To create many objects, we'll need to utilize a class. A class is a type of blueprint used to design the structure and layout of an object. We need to design what our objects have, their attributes, and what they can do, their methods. We will create a class of car. We will create some car objects. Class car. To construct a car object, we need a special type of method called a constructor. It works similarly to a function. We will define a function of double underscore init, meaning initialize, double underscore again, and then follow this with a set of parentheses. This is our constructor method. We need this method in order to construct objects. It's a dunder method, dunder meaning double underscore. That's a future topic. I don't want you to be overloaded with information right now. All you need to know is that we need this method in order to create objects. This method behaves similar to a function. We need to set up the parameters. Self is already provided to us. Self means this object we're creating right now, this car. So what are some attributes that a car should have? A model, that could be a string, like a BMW. A year, that could be a number. A color. Let's add a boolean of for sale. Is the car for sale or not? That's true or false. To assign these attributes, we're going to access self. Self dot the name of the attribute. Self dot model equals the model we receive. These are parameters. When we receive the name of a model, we will assign it to this object. Let's do this with year. Self dot year equals year. Self dot color equals color. Self dot for sale equals for sale. This is an example of a few attributes that a car might have. A model, year, color, and if it's for sale or not, represented by a boolean. Now, to construct a car object, we need a unique name for this car. Let's just say car1. Car1 equals, take the name of the class, add a set of parentheses to invoke the constructor. We're going to do this almost exactly like a function. We have parameters set up. We need to send a matching number of arguments. Self is provided to us behind the scenes automatically. We need a model, year, color, and if it's for sale or not. So pick a car of your choosing. I'll pick my favorite car. The model will be a Mustang. For the year, I'll go with the recent year of 2024. A color, I'll pick red. Is the car for sale? I like this car, so no. I will set that to be false. Make sure false is capitalized. Let's see what happens if I attempt to print our car object of car1. What we're given is the memory address of this car object, where it's located. But I would like one of the attributes located at this memory address. Instead of printing the object itself, we're going to access one of the attributes found within this car. We will follow the name of the car with a dot. This dot, it's known as the attribute access operator. I would like the model of car1. That would give me Mustang. Let's access the year. Take the name of the car, car1, dot, the year, 2024, followed by the color, car1, dot color, red. Car1, is it for sale? We'll print that. That is false. Now let's create a second car. We're going to reuse this class to create a second car. We will create car2 equals car. We'll pass in some different arguments. A Corvette. The year will be 2025. The color will be blue. Is this car for sale? Let's say that is true. Instead of accessing car1's attributes, let's access car2's attributes. That would give us a Corvette. The year is 2025. The color is blue. For sale is set to true. Or even a third car. Car3 equals a new car. We will pass in a string of Charger. The year, 2026. The color will be yellow. Is this car for sale? Let's say that is true as well. Then I will print car3's attributes. The model is Charger, the year is 2026, the color is yellow, for sale is set to true. With classes, they can take up a lot of space. For better organization, you can place them within a new Python file. So let's cut our class, and we will create a new Python file within our project folder. File, new, Python file. The name of this Python file is going to be all lowercase, car. Then we will paste the class that we cut originally. Class car, which has a capital C. So from our main Python file, we're going to import our car file, our car module. From the name of the module, car, import the name of the class, car. Then when I run this program, nothing should change. We should still have access to all of our car objects. You could either keep your classes within your main Python file, or import them if you would like to organize things. Let's talk about methods. Methods are actions that our objects can perform. Within our class, we will define a method of drive. Self is going to be provided to us. When we invoke the drive function, let's print you drive the car. What other things can cars do? Let's stop. We will print you stop the car. Let's take car1, access the drive method. You drive the car. Car2 also has a drive method. You drive the car. Same thing with car3. You drive the car. Let's access the stop method. Car1 dot stop. Car2 dot stop. And car3 dot stop. These methods are identical for each car object. Instead of printing the word car, let's insert the model of the car. I will convert these print statements to F strings. Instead of the word car, let's add a placeholder. Let's add self.model. Self is referring to the object we're currently working with. Use the attribute access operator, followed by the name of the attribute. Let's also do this with the stop method. Self dot model. Let's take car1, use the drive method. You drive the Mustang. Car1 dot stop. You drive the Mustang, you stop the Mustang. Let's do this with car2. You drive the Corvette, you stop the Corvette. Car3. You drive the Charger, you stop the Charger. Now, within our F strings, let's insert the color. I'll add a placeholder, self.color. Do this with stop as well. Self.color. You drive the yellow Charger, you stop the yellow Charger. Car1. You drive the red Mustang, you stop the red Mustang. Car2. You drive the blue Corvette, you stop the blue Corvette. Let's add one last method. Let's create a method to describe our car. We'll print the details of the car. Let's print, I'll use an F string, add 3 placeholders. Let's print self.year, followed by self.color, then self.model. We'll take car1, use the describe method that we created. Describe car1. Car1 is a 2024 red Mustang. Describe car2. Car2 is a 2025 blue Corvette. Car3 is a 2026 yellow Charger. All right, everybody, so those are objects in Python. An object is a bundle of related attributes. Attributes are variables that an object has. And methods. Methods are functions that belong to an object. They define what this object can do. And well, everybody, that is a summary of object-oriented programming using Python. Hey everybody, today I gotta talk about class variables in Python. Class variables are shared among all instances, meaning objects, created from a class. Instance variables are defined inside of the constructor. Class variables are defined outside of the constructor. With class variables, they allow you to share data among all objects created from the class. With instance variables, each object has their own version. With a class variable, all those objects share one variable. Here's an example. We will create a class of student. We also need a constructor. When we create a student object, this constructor is automatically going to be called, but we need to pass in some arguments. We are provided with self. Self refers to the object we're currently working with. We will set up a name parameter and an age parameter. We will assign self, the object we're currently working with, set the name attribute to equal the data for the name that we receive from this parameter, and self.age equals age. Let's construct 2 student objects. We will have student1 equals, then call the constructor for student. So type the name of the class, followed by a set of parentheses to invoke it. This will automatically call the constructor, but we have to pass in data for the name and the age. For the name, let's pass in SpongeBob, because basically everybody in the world knows who SpongeBob is. I don't know how old SpongeBob is, we'll say he's 30. We'll create another student object, which we will refer to as student2. We will call the constructor of our student class, pass in data for the name and age. Student2 will be Patrick. Patrick will be 35. Okay, let's make sure this works. Let's print student1's name followed by student1's age. And we should get SpongeBob and his age is 30. Let's print student2's name and student2's age. Patrick is 35. Now we'll create a class variable. Class variables are defined outside the constructor, and they are shared among all objects created from that class. Each object has their own name and age property. These are instance variables. But class variables are defined outside the constructor. Each object will share this one variable. So if we're working with students, let's say there is a class variable of class year. What is the graduating year of this class? 2024. Now, let's print student 1's graduating year. Print student 1 dot class year. Okay, so SpongeBob has a class year of 2024. That's when he's graduating. Let's check student 2. Patrick, his age is 35. His graduating class year is 2024. Now, with class variables, you can access them through any one object, such as student 1 or student 2. It's good practice to access a class variable by the name of the class, rather than any object created from the class. Since we're accessing class year, we'll access this class variable by the name of the class of student. Make sure the S is capital. This helps with clarity and readability. If I was looking at this print statement, I can tell that class year is a class variable because we're accessing it directly from the class, and not any instance from this class. Without looking at this class, I can't tell if class year is an instance variable or a class variable, but if I access it via the class name, it's more explicit. So it's good practice to access a class variable by the class name itself, and not any one instance of this class. Let's create another class variable. We'll create a class variable to keep track of how many students we have created. This class variable will be num students, meaning number of students, equals 0. So within our constructor, we can write any code that we want. This code will always be executed when we instantiate an object. I would like to take our number of students and increment it by 1 each time we construct a new student object. So instead of using self refers to the object we're currently working with. If we're constructing student 1, just imagine we're replacing self with student 1, or student 2 if we were constructing student 2. If we're going to be modifying a class variable, in place of self, we'll use the name of the class, student. Access our class of student, get the class variable of number of students, then I will increment it by 1, plus equals 1. We are constructing two student objects. I will print access our class of student, get the number of students, and print it. We're constructing two student objects. If I print the number of students that we have, it should be 2. Then, just to be sure that this is working, let's construct a third student object. Student 3 equals student. This student will have a name of Squidward. Squidward's age will be 55. Now we have 3 students. And for good measure, let's construct one more. Student 4 equals, we will create a new student with a name of Sandy. Sandy's age will be 27. The number of students is now 4. Just as an exercise, using an F string, let's print the student class's class year as well as the number of students. I will print, use an F string, my graduating class of, let's add a placeholder, access the class of student, then access the class year. My graduating class of 2024 has, then we need the number of students. We'll add a placeholder, access the class of student, access the number of students, has blank students. Let's see if this works. My graduating class of 2024 has 4 students. Now, if I were to change 2024 to 2025, my graduating class of 2025 has 4 students. Let's print the name of each student. These are instance variables. Student1.name, Then we need student 2, 3, and 4. My graduating class of 2025 has 4 students: SpongeBob, Patrick, Squidward, Sandy. Alright everybody, so those are class variables. Class variables are shared among all instances of a class. They are defined outside of the constructor. The benefit is that they allow you to share data among all objects created from that class. And well everybody, those are class variables in Python. What is going on everybody? So today I gotta talk about inheritance in Python. Inheritance allows a class to inherit the attributes and methods from another class, much like how a child in real life can inherit traits from a parent. By having a class inherit attributes and methods from another class, this helps with code reusability and extensibility. In this example, we're going to create an animal class. The dog, cat, and mouse class will inherit attributes and methods from the animal class. We will create a class of animal. Then I will define the constructor. When we construct an animal object, let's pass in a name. It's not required, but it might be good for this example. We will assign the attribute of name equal to the name we receive. Let's also add an attribute of is alive. Whenever we create an animal, we will set their is alive attribute to be true, and that is a capital T. All animals can eat. Define eat. We will print, using an F string, add a placeholder, self.name, the name of this animal, is eating. All animals should be able to sleep. Define sleep. Print, I'll use an F string, insert self.name is sleeping. And that is all we need for the animal class. Let's define class dog. For a child class to inherit the attributes and methods from another class, after the class name that's going to inherit, we need to add an inheritance list with a set of parentheses, then list the name of the class we're inheriting from, the parent. The dog class is going to inherit all of the attributes and methods of its parent, animal. For the time being, as a placeholder, I'll add pass, just to demonstrate this. Class cat is also going to inherit from animal. And class mouse will also inherit from animal. Okay, I will collapse this for now. We'll create a dog object, dog equals dog, then pass in a name for this dog, because we have one parameter set up of name. This dog will be named Scooby, as in Scooby-Doo. Cat equals, call the cat constructor. This cat will be named Garfield. And mouse. Mouse equals mouse. Our mouse will have a name of Mickey. Even though there's nothing within this dog, cat, or mouse class, we should still have these attributes and these methods. If you inherit the animal class, you should have a name attribute, an is alive attribute set to true, you can eat, and you can sleep. Let's print our dog's name. Dog.name. Scooby. Print dog.is alive. Our dog is alive. That is true. Let's have our dog object use the eat method. Scooby is eating. And sleep. Dog.sleep. Scooby is sleeping. Let's replace dog with cat. The name of the cat is Garfield. Garfield is alive. Garfield is eating. Garfield is sleeping. And mouse. Replace any instance of cat with mouse. Our mouse's name is Mickey. Mickey is alive. Mickey is eating. Mickey is sleeping. Even though these children classes are empty, we're still inheriting these attributes and methods from its parent, of animal. This is convenient because you don't need to copy and paste these attributes and methods for every single class. For example, if I were to copy these attributes and methods and paste them, Well, we have a lot more code to write. And as a consequence, if I need to make a change to one of these methods, I would have to do that to every single instance of this method. For example, let's replace is sleeping with is asleep. Well, now I need to find every single sleep method and change it manually. It's not too bad if you only have a few classes, but imagine if you have hundreds of classes. That's going to take a lot of work. It's a lot easier to write the code once and then reuse it, and I only need to make that change in one place, rather than make that change many times. So let's change is sleeping to is asleep, and see if that works again. Mickey is asleep. Let's replace mouse with dog. Scooby is asleep. Not only that, but with children classes, they can have their own attributes and methods that are different from one another. So dogs have all these attributes and methods, and they can speak. Let's create a speak method, and I will print a unique message for dogs. Woof. Cats will also have a speak method, but it's going to be different. Cats will meow. Then for our mouse class, they will squeak. Let's have our dog speak. Woof. Let's have our cat speak. Meow. And our mouse. Squeak. Alright everybody, so that's an introduction to inheritance. Inheritance allows a class to inherit attributes and methods from another class. Much like in real life, a child can inherit traits from a parent. These are also known as sub and superclasses, which is a topic for another day. Inheritance helps with code reusability and extensibility. If all of these children classes inherit these attributes and methods from another class, we only need to write that code once and not copy it for every single class that needs it. We can write and change the code in one place for better reusability and extensibility. And well, everybody, that is an introduction to inheritance in Python. Hey everybody, so today we got to talk about both multiple and multi-level inheritance. We'll begin with multiple inheritance. That's when a child class inherits from more than one parent class. For example, a class of C can inherit the traits from both class A and B. In Python, you can have more than one parent. Multi-level inheritance, we'll talk about near the end of this topic. So in this example, we're going to create two parent classes, prey, I'll write pass for now, and predator. We'll create a class of rabbit, a class of hawk, then class fish. Rabbit, hawk, and fish are going to be children classes. Prey and predator will be parents. If one of these classes, rabbit, hawk, or fish, inherit from prey, they get the ability to flee. We will define a method of flee. All we'll do in this example is print the following text. This animal is fleeing. If you're a predator, you get the method to hunt. Define hunt. We will print this animal is hunting. Rabbits, they will inherit from the prey class. They're typically not predators, except that one rabbit in Monty Python and the Holy Grail. That's the exception. Rabbit will inherit the prey class. Then it gets access to a flee method. Hawks are predators. They will inherit the predator class. Now fish, they will hunt smaller fish and flee from bigger fish. You could consider fish both prey and predators, so they will inherit both classes. We will use multiple inheritance. They will inherit everything from the prey class and the predator class. Now let's see if this does in fact work. Now we'll create a rabbit object. Rabbit equals rabbit. There are no parameters set up. We don't need to send any arguments to the constructor. Hawk equals hawk. And fish equals fish. So let's take our rabbit object, and they should have a flee method. Rabbit.flee method. This animal is fleeing. But they do not have a hunt method because they're not predators. Rabbit object has no attribute hunt. Hawks can hunt. They're predators. They inherited that method. This animal is hunting, but they can't flee. They're not prey. Hawk object has no attribute flee. Fish can do both. They inherit from the prey class and the predator class. Fish.flee. This animal is fleeing. Fish.hunt. This animal is hunting. Children classes can inherit from more than one parent, which is what we did for fish. They are both prey and predators, whereas in rabbits are just prey, hawks are just predators. If you need to inherit from more than one parent, you just add that additional class to the inheritance list. With multi-level inheritance, a parent can inherit from another parent. We will create a class of animal. And for now, I'll write pass. Prey and predator are going to inherit from the animal class, so we need to add animal to each inheritance list. Let's say if you're an animal, you get a method to eat. All animals will eat. Print this animal is eating. And you can sleep. Define sleep. Print this animal is sleeping. So think of rabbit, hawk, and fish as children classes. Prey and predator are those classes' parents, and animal is the grandparent. Prey and predator will inherit everything that the animal class has. Rabbit, hawk, and fish will inherit everything the prey and predator classes have. So now our rabbit, hawk, and fish classes should have the ability to eat and sleep, and we'll test that. Rabbit.eat. This animal is eating. Rabbit.sleep. This animal is sleeping. Let's check out fish. Fish.eat. This animal is eating. Fish.sleep. This animal is sleeping. Okay, we're going to expand upon our example a little bit. Let me zoom out. Each of our objects is going to have a name. Our rabbit will have a first name of Bugs. Hawk will be Tony, as in Tony Hawk. Our fish will be Nemo. Within our classes, we don't have any constructors set up. In which class should we assign the name attribute? Let's do so within our animal class. So we will define a constructor to assign these attributes. We will receive a name. We'll assign self.name equals name. Now with these other classes, if you're not assigning any attributes, or if you don't need any other initialization logic, you don't need a constructor. We'll implicitly use the constructor we inherit from the parent. Let's convert each of these print statements to an f-string. Replace animal with self.name. Now let's have our rabbit use the eat method. Oh, we should get rid of this. There we go. Bugs is eating. Rabbit.sleep. Bugs is sleeping. Rabbit.flee. Bugs is fleeing. Let's check out our hawk. Hawks don't have a flee method because they're predators, not prey. Let's eat. Tony is eating. Let's sleep. Tony is sleeping. Let's hunt. Tony is hunting. Let's check our fish next. Our fish can eat. Nemo is eating. Our fish can sleep. Nemo is sleeping. They can flee. Nemo is fleeing. And hunt. Nemo is hunting. Okay, everybody, that is both multiple and multi-level inheritance. With multiple inheritance, A child can inherit from more than one parent class. You just add each additional class to the inheritance list. With multi-level inheritance, a child can inherit from a parent, which inherits from another parent. Class C can inherit from B, where Class B inherits from A. Think of C as the child, B as the parent, and A as the grandparent. C will have all the attributes and methods, even available within the grandparent class of A. And well, everybody, that is both multiple and multi-level inheritance in Python. Hey everyone, welcome back. So today I got to talk about abstract classes in Python. An abstract class is a class that cannot be instantiated on its own. Abstract classes are meant to be subclassed. They're supposed to be parents to children classes. They can contain abstract methods, which are declared, but have no implementation. Abstract classes have a few benefits. We can't create an object from a class that's abstract. Abstract classes, you could say, are incomplete. We don't want to create an object that's incomplete. Also, any children that inherit from an abstract class, if there's any abstract methods, we have to implement them. So let me give you a demonstration. We're going to create a class, a vehicle. For now, I'll write pass. To work with abstract classes, we'll need to import ABC. ABC meaning abstract base classes. We need import ABC, all capital meaning abstract base class, as well as abstract method. So my vehicle class, it's going to be an abstract class. We will inherit from ABC, the abstract base class. I don't want myself or any other developers to be able to create a vehicle object. I will make this vehicle an abstract class. Also, I can add some abstract methods. These methods will be inherited by its children. To declare an abstract method, we need to use a decorator at abstract method. So what should all vehicles be able to do? Let's say go and stop. If you're a vehicle, you can go. With abstract methods, we declare them, but we don't define them. We'll define them within each of the children classes that inherit from vehicle. Let's create another abstract method. Abstract method define stop. If you're a vehicle, you can stop. All right, we have finished our abstract class, a vehicle. Just to demonstrate that we can instantiate an object from this class, let's attempt to do so and see what happens. I will attempt to create a vehicle object. Vehicle equals vehicle, and then run this. Type error, can't instantiate abstract class vehicle with abstract methods go and stop. This is good. This is what we want. Our vehicle class is incomplete. We don't want to accidentally make a vehicle object. If we were, it's kind of like the invisible boatmobile from SpongeBob. Instead, we will create some children to inherit from this class. So now we will create a class of car, which will inherit from vehicle. Car is the child, vehicle is the parent. But we are receiving a warning. Class car must implement all abstract methods. What we're saying is, hey, if you inherit from the vehicle class, you need to include these abstract methods. So I'm not going to currently. Let's just see what happens. I will attempt to create a car object and run it. Type error, can't instantiate abstract class car with abstract methods go and stop. If a class is inheriting from a parent that's abstract and there's abstract methods, we have to finish defining those methods. So within our car class, really I'll just copy this because I'm lazy. Our method is go. We will print you drive the car. We also need stop. I will print you stop the car. Okay, let's see if this works. This has run with no problems. I will have my car go, then stop. We're calling the go method, then the stop method. You drive the car, you stop the car. Let's create a few more children for the vehicle class. Class motorcycle will inherit from the vehicle class. Again, we have to implement the abstract methods found within the parent, go and stop. For go, I will print you ride the motorcycle. Then with stop, you stop the motorcycle. Motorcycle equals motorcycle. We're calling the constructor. Then I will have our motorcycle go, then stop. You ride the motorcycle, you stop the motorcycle. All right, last example. Let's say we create a boat class, which will inherit from the abstract class a vehicle. I will include a go method, where I will print you sail the boat. But I will forget to add a stop method, because I'm not paying attention. Let's attempt to create a boat. Well, what the heck is this? Type error, can't instantiate abstract class boat with abstract method stop. Then I'll look over my code and see, oh, I forgot to include a stop method. With including abstract methods within a parent, it acts as a set of checks and balances. All vehicles should be able to go and stop. If I forget to define one of these methods, well, we'll receive a type error. If we didn't, I may not have noticed that we're missing a method. So now we need to include that stop method. I will print you anchor the boat. This seems to have run with no problems. I will have my boat go and stop. You sail the boat, you anchor the boat. All right, everybody, so those are abstract classes. It's a class that can't be instantiated on its own. We can't create any objects from this class. We don't want to because it's, well, incomplete. They're meant to be subclassed. They can contain abstract methods, which are declared, but we don't finish defining them. We define them within the children classes. In this example, car, motorcycle, and boat. And well, everybody, those are abstract classes in Python. Hey, everybody. So today I got to talk about the super function in Python. Super is a function. It's used within a child class to call methods from a parent class. The child class is the subclass. The parent class is the superclass, hence why this function is named the superfunction. Using the superfunction, it allows you to extend the functionality of the inherited methods. Here's an example. We'll create a few shape objects. We'll need to set up the classes though. We'll have class, circle. For the time being, I'll just write pass. We'll fill it in later. Class, square, and class, triangle. For each of these classes, in order to instantiate objects, we'll need a constructor. We will define our constructor, our init method. When creating circles, what sorts of attributes should a circle have? Let's say a color. What's the color of the circle? Is it filled or not? Filled will be another attribute. And a radius. Then let's assign these. Self.color equals the color that we receive. Self.filled equals filled. Self.radius equals radius. Let's do this with the square and triangle. Really, I'll just copy our constructor and paste it. Squares don't have a radius. With a square, the width and the height are the same. Let's replace radius with width. We'll also keep the color and filled attributes. Self.width equals width. Now with triangles, again, let's copy our constructor. We'll need a width and a height. Self.height equals height. So with programming, we try not to repeat ourselves if we don't have to. What do all of these classes have in common? They all share the attributes of color and filled. The ways in which they are different is that circle has a radius attribute, square has a width, triangle has a width and a height. If we have to make any changes to one of these attributes, we would have to do so manually. For example, let's replace filled with isFilled. Now I need to look throughout my code for any instance of filled and replace it with isFilled. It's a lot of work, and I might make a mistake, such as here and here. It's better to write your code once and try and reuse it. So that's where inheritance and the super function can come in handy. We're going to take the attributes of color and isFilled and place it within a parent class. These children classes will inherit those attributes. So class, what do they all have in common? They're all shapes. Class, shape. And for now, I'll write pass. Circle is going to inherit from its parent of shape. That also applies with square and triangle. We'll set up a constructor for shape. Define init. We will pass in the color and isFilled. Then we will assign these attributes. Self.color equals color. Self.isFilled equals isFilled. We don't need to manually assign these attributes within each of these constructors for the children. Instead, what we have to do is within the constructor for each of these children classes, we have to call the constructor for the parent, also known as the superclass of shape. So we will eliminate these two lines of code, use the super function, dot, call the constructor of the parent. And that is the dunder init method. But we need to pass in the color that we receive and isFilled. This will be a Boolean. Then let's do this with the square class and the triangle class. We still need radius for the circle, width for the square, width and height for the triangle. We're going to call the super function to take care of whatever attributes all these types of shapes have in common, such as color and isFilled. Now let's see if this works. Let's construct a few objects. We will create a circle named circle, call the constructor for circle. We have to pass in a color, a Boolean if it's filled or not, and a radius. So for the color of the circle, let's say red. isFilled, let's say that is true, and a radius of 5. You could even use keyword arguments for better readability, although not necessary, but for clarity, let's say color equals red, isFilled equals true, radius equals 5. Let's see if this works. I will print our circle's color. It is red. Print our color's isFilled attribute. The circle is filled. That is true. And the radius. Print circle dot radius. The radius of the circle is 5. We could even convert this to an F string. I'll add a placeholder, then add centimeters. 5 centimeters. Let's construct a square object. Square equals square. We'll need a color, isFilled, and a width. I'll just copy what we have and make a few changes. Replace radius with width. The color will be blue. isFilled will be false. The width will be 6. We don't need a height because squares have an even width and height. If we ever need the height, we can assume it's the same as the width. In this case, 6. Let's check out our square. Square.color, square.isFilled, square.width. Our square is blue. It's not filled in. The width is 6 centimeters. Let's create a triangle object. Triangle equals triangle. Pass in our arguments. The color will be yellow. isFilled will be true. The width will be 7. And the height will be 8. Let's print our triangle's color. Is it filled? Its width and its height. Our triangle is yellow. It's filled in. The width is 7 centimeters. The height is 8 centimeters. So that's how you can use the super function to reuse the constructor of a parent class. We don't need to manually assign each of these attributes within each of the children classes. We can do that in just one place. When we refer to super, imagine that we're replacing this with the parent class name, such as shape. That might be a good way to think of it. Use the constructor of the parent class of shape and pass these arguments in. What you could do as well is extend the functionality of a method. So within our shape class, let's create a method of describe. We will describe the attributes of this shape. We will print, use an f string. When we want to describe our shape, let's say it is, add a placeholder, self.color. What is the color of this shape? And is it filled or not? And add a placeholder. We'll use a ternary operator. Print filled if self.isFilled is true. Else we will print not filled. Each of these types of shapes, circle, square, and triangle, will have access to a describe method. Let's attempt to use it. Take our circle, use the describe method that's inherited. It is red and filled. Square. It is blue and not filled. Triangle. It is yellow and filled. So then we also have method overriding. What if we create a similar method of describe within circle, square, and triangle? Let's do that. Define a describe method. Within our circle, let's calculate the area. What's the area of the circle? I'll use an f string. It is a circle with an area of, then we'll calculate the area given the radius. To calculate the area of a circle, we can take pi, I'll just say 3.14 just to keep it simple, times the radius squared. Self.radius times self.radius. If I were to call the describe method, will we use the parent's version of describe or the child? So let's take our circle, use the describe method. The result? It is a circle with an area of 78.5. I should really add centimeters squared after that. Centimeters squared. This is called method overriding. If a child shares a similar method with a parent, you'll use the child's version and not the parent's. This is method overriding. If you would like to extend the functionality of a method from a parent, you can use the super function. Not only do I want to use the describe method of the child, I would also like to use the describe method of the parent. So within this function, we will use the super function. Access the describe method of the parent. What we're doing is extending the functionality of the describe method. It is a circle with an area of 78.5 centimeters squared. The circle is red and it's filled. Or you could change up the order. Let's use the parent class's describe method and extend the functionality with our own print statement. It is red and filled. It is a circle with an area of 78.5 centimeters squared. Let's finish this with the square and triangle classes. I'll copy what we have for the describe method within the circle class, but we'll make a different calculation. Describe the square. It is a square with an area of, take self.width times self.width. The height and the width are going to be the same if it's a square. Then describe our triangle. It is a triangle with an area of width times height, we have a height in this case, divided by 2. We've already described our circle, let's describe our square. It is a square with an area of 36 centimeters squared. It is blue and not filled. Let's describe our triangle. It is a triangle with an area of 28.0 centimeters squared. It is yellow and filled. Alright everybody, that is the superfunction. It's used in a child class to call the methods from a parent class, also known as the superclass. It allows you to extend the functionality of the inherited methods. Within a child class, you could use it within a constructor to assign any attributes that all of its siblings have in common, such as color, or if that shape is filled. When used within any other method, you can extend the functionality of that method. Not only are we printing this message from the parent, we're tacking on another print statement before that. And well everybody, that is the superfunction in Python. What is going on everybody? So today I gotta talk about polymorphism in Python. Polymorphism is a programming concept. It's a Greek word that means to have many forms or faces. Poly means many, morph means form. In programming, an object can take one of many forms. There's two ways to achieve polymorphism. One is through inheritance. An object could be treated of the same type as a parent class. There's also duck typing, which we'll talk about in the next topic. In this video, we're more focused on inheritance. What we'll do in this video is create a class of shape. We'll write pass as a placeholder. We will create a class of circle, which will inherit from shape. Again, writing pass. Class square inherits from shape. Class triangle, which inherits from shape. If I was to create a circle object, circle equals circle. Our circle identifies as a circle, and since our circle class inherits from the shape class, our circle is also considered a shape. It has two forms. It's a circle, and it's a shape. But our circle isn't a square or a triangle. That could also apply to our square class. Our square is a square. Our square is also considered a shape, but our square is not a circle or a triangle. Those are two possible forms for our square. It's a square and a shape. So let's say we would like to create a list of shapes. What do they all have in common? Well, they're all shapes. A descriptive name for this list would be shapes equals an empty list. I will instantiate a circle object, a square object, and a triangle object. Our circle is a circle and a shape. Our square is a square and a shape. Our triangle is a triangle and a shape. Each of these objects has two forms, or two faces. Let's fill in some of these classes. Let's say that with our shape class, we will define an area method. Define area. I'm going to turn this into an abstract method. I'll just write pass. To work with abstract classes, we need to import that. From ABC, import capital ABC, as well as abstract method. Preceding the area method, I will add a decorator of abstract method. Our circle, square, and triangle classes, they're all considered shapes. They inherit from this class. We need to define an area method for each, since they're all considered a shape. Every shape has an area. With our class of circle, let's define a constructor. Define init. We will pass in one argument, a radius. What is the radius of the circle? Assign an attribute of radius equals the radius we receive. Let's do this with square. Define init. One parameter, the length of a side. Self.side equals side. Then triangle. Define init. We have two parameters, base and height. Self.base equals base. Self.height equals height. Alright, now let's finish defining these area methods for each class. We will return 3.14 times self.radius to the power of 2. So given a radius, that's how to calculate the area of a circle. Then with our square, define area, we will return self self.side to the power of 2. Then with our triangle, define area, return self.base times self.height times 0.5. Now we have to pass in some arguments. For our circle, we need a radius. I'll pick 4. For the square, the length of a side will be 5. Then our triangle, the base will be 6, the height will be 7. We're going to write a loop to iterate through our shapes. For every shape in shapes, then we're going to print for every shape, call the area method. And that would give me these numbers. If you would like, you can format the output. I'll just use an F string. I'll add centimeter squared. Much better. What if we were to create a class that's completely unrelated to shapes? I will create a class of pizza. I will define a constructor. To construct a pizza object, we need a topping and a radius. What is the radius of the pizza? Self.topping equals topping. Self.radius equals radius. Within my list of shapes, I'll add a pizza object. But I have to pass in a topping, such as pepperoni. And what is the radius of the pizza? Let's say 15 centimeters. So our pizza class doesn't have an area method. Here's what happens when I run this. We get an attribute error. Pizza object has no attribute area. Our pizza object is considered a pizza, but it is not considered a shape. It does not inherit from the shape class at the top here. You know what? A pizza is circular. It could be considered a circle. So how about this? Let's take the pizza class. It will inherit from the circle class. And within our circle class, we're already assigning the radius to the radius attribute. So instead of doing that here within the constructor for our pizza class, let's call the super constructor. Super, which refers to the parent, use its constructor, then pass in the radius we receive. Let's see if this works now. That does. Here is the area of our pizza. Our pizza is considered a pizza. It inherits from the circle class, so it's also considered a circle. And our circle class inherits from the shape class. Our pizza has 3 forms. Our pizza is considered a pizza. It's also considered a circle, and it's also considered a shape. It would make sense for it to fit into this list of shapes, because our pizza also identifies as a shape. So that's polymorphism, everybody. It's a Greek word meaning to have many forms or faces. Poly meaning many, morph meaning form. In Python, there's 2 ways to achieve polymorphism. One through inheritance. An object could be treated of the same type as a parent. And there's also duck typing, which we'll discuss more in the next topic. Stay tuned for that. And well, everybody, that's polymorphism in Python. Hey everybody, so today I gotta talk about duck typing in Python. Duck typing is another way to achieve polymorphism besides using inheritance. Objects can be treated as if they're a different type, as long as they meet the minimum necessary attributes and methods required of them. It follows this adage: if it looks like a duck and quacks like a duck, it must be a duck. As long as an object resembles another, it could also be treated of that type. So in this example, let's create a class of animal. We will have a class attribute of alive. If you're an animal, you will have an attribute of alive. You're a living creature. Let's create a class of dog. The dog class will inherit from the animal class. They will inherit the alive attribute. Let's also define a speak method. If you're a dog, you gain the ability to speak. We will print woof. Then we'll create a cat class. Class cat inherits from animal, For the speak method, we will print meow. Let's create a list of animals. What do these two classes have in common? They both could be considered animals. Let's create a list of animals. We will construct a dog object and a cat object. If I was to write a for loop for every animal in my list of animals, have each animal use its speak method, which will result in the dog going woof, the cat going meow. They're both speaking. What if we add a class that has nothing to do with animals? Like class car. Cars will have a horn method. That's how they speak. When you honk the horn, you will print honk. Within my list of animals, let's create a car object. It really doesn't belong in here, but let's see what happens. We have an attribute error. Car object has no attribute speak. Our car object doesn't have the minimum necessary attributes and methods. When iterating through this list of animals, we're calling each animal speak method, which our car object doesn't have, but it does have a horn method. So what if we rename our horn method as speak? Maybe it's an AI car or something. Well, this would work. The dog goes woof, the cat goes meow, the car goes honk. So our car object, it quacks like a duck. We could consider it a duck. It has the minimum necessary methods to be considered an animal. Animals inherit this alive attribute. Let's utilize that. After the animal speaks, let's print their alive attribute. Print my animal's alive attribute. My car object doesn't have that attribute. We get an attribute error. Car object has no attribute alive. But if I was to add that attribute, alive equals false, we have true for the dog, it's living, true for the cat, it's living, but false for the car, it's not living, it's not a living creature. My car meets the minimum necessary requirements to be considered an animal. If I were to set this to be alive, well, then it would be a living car, kind of like the movie Cars. So with Python, duck typing is another way to achieve polymorphism besides using inheritance. As long as an object has the minimum necessary attributes and methods, you could treat it as a different type of object. If it looks like a duck and quacks like a duck, it must be a duck. And well, everybody, that is duck typing in Python. Hey, what's going on, everybody? So in today's video, I'm going to explain aggregation in Python. Aggregation represents a relationship where one object contains references to one or more independent objects. One object acts as a container, the whole, which can contain other objects, the parts. So what we'll do in this demonstration is create an object that's going to act as a container. We'll create a class of library. For now, I'll write pass. Now, a library can contain books. We will create a class of book. We'll be creating book objects, which we will add to our library object. The library object is going to act as the whole, the container. The books are the independent parts. A library can exist without its books, and the books can exist without the library. That's the main difference between aggregation and composition. These classes are independent of one another. They can exist without each other. With our class of book, we'll need a constructor. We will define our constructor. If we create a book, we need a title and an author. We will define a title attribute equals the title that we receive. And self.author equals the author that we receive. That's all we need for the book class. Now with the library class, we will also need a constructor. Define init. For our library, we need a name for the library. For example, the New York Public Library. Self.name equals the name that we receive. Let's construct our library object first. Library equals library. We need to pass in a name for this library. Let's say New York Public Library. So this should run with no problems. Then we'll create a few books. Let's say book 1 equals, call the book constructor. We have to pass in a title and an author. So pick a few books. I will pick Harry Potter. Harry Potter and the Philosopher's Stone, but I don't want to type the whole title. Let's just say Harry Potter ... The author of this book is J.K. Rowling. Okay, let's create another book. Book 2 equals book. For my next book, I'll pick The Hobbit. The author is J.R.R. Tolkien. Then book 3 equals book. We need a title and an author. I will pick The Color of Magic by Terry Pratchett. We have no problems when running this. Our library and our books can exist without each other. Our books are independent. So now where aggregation comes in, our library object will contain our book objects. One way in which we can handle this is that within the constructor for our library, let's create an attribute of books. This will be an empty list. We'll need a way to add these books to our list of books. We will define a method of add book. But we have to pass in a book object when we call this method. We're going to access self.books. It's a list. Lists have a built-in append method. We will append our book to our list of books. Let's see if this at least runs. We're going to take our library, call the add book method that we defined, then pass in our book object of book 1. Then let's do this with book 2 and book 3. And this is run with no problems. Our books can exist independently of our library. Our library object is just containing them. It's housing these books. Now, if I would like to print all the books in my library, I could create a method to do that. Let's define a method of list books. There will be no parameters besides self. I'm going to return a list comprehension for every book in self.books. Remember that books is a list. For every book in books, let's return an f string where we display the book's title and the book's author. Display book.title, the word by, book.author. Okay, let's see if this works. First, I'm going to print the library's name. Print library.name, New York Public Library. Then I'm going to print access the library objects list books method. And here's my list of books. Although I'm going to reformat this so it looks better. I'll use a for loop. For every book in access our library objects list books method, this will return a list. We can iterate through it. For every book in the list of books, print each book. All right, here is our library's name and each book in our list of books. All right, everybody, so that's aggregation. It represents a relationship where one object, the whole, contains references to one or more independent objects, the books. They can exist without one another. And well, everybody, that is aggregation in Python. All right, everybody, so today I got to talk about composition in Python. As we've discussed in the previous topic, Aggregation is a relationship where one object contains references to other independent objects. They have a has-a relationship. Composition, on the other hand, is when the composed object directly owns its components, which cannot exist independently. They have a owns-a relationship. Aggregation has things. Composition owns things. Kind of like you're renting or you're owning something. In this example, we'll create three classes. A class of engine, a class of wheel, and the composed object is going to be class car. Within our car class, we will construct some engine and wheel objects. We'll begin with our engine class. We'll need a constructor. We'll define that. Define init. Let's say that with an engine, we need a horsepower. What is the power of the engine? Self.horsepower attribute equals the horsepower that we receive. With our class of wheel, we need a constructor. Define init. Let's add a size attribute. What is the size of the wheel? Self.size equals size. Okay, now with our car object. Now within our car class, we need a constructor. We will need a make model, the horsepower of the engine, and size. We'll say wheel size. Remember that you can rename parameters to something different. We will assign these attributes. Self.make equals make. Self.model equals model. Here's where composition comes in. We will define an attribute of engine, then call the engine constructor. We have one argument to pass in, horsepower. We will pass in the horsepower that we receive to the engine constructor. Then we have to set up our wheels. Self.wheels equals. Now to construct a single wheel object, we would call the wheel constructor, then pass in the wheel size. However, cars have 4 wheels. We don't want just one wheel. So what we could do is write a list comprehension. For every wheel in range 4 to iterate 4 times, let's call the wheel constructor and pass in our wheel size. This list comprehension will create 4 wheel objects for us. The reason that this is considered composition, we're creating engine and wheel objects inside of this class car. Our class car owns an engine and owns 4 wheels. We're not creating these objects outside of the car class. Let's create a car object. Car equals car. We need a make model, horsepower for the engine, and wheel size. So for my car, let's say Ford Mustang. For the horsepower, I'll make up something, 500. For the wheel size, 18 inches. Now, just to make this more explicit, I'm going to use keyword arguments, but you don't have to. So make equals Ford, model equals Mustang, horsepower equals 500, wheel size equals 18. Let's create a method to display our car. I would like the details. Define display car. No parameters. Let's return an F string. Let's begin with the make and model. Those will be easy. Display self.make and self.model. Let's take our car object, use the display car method. Then I gotta print it. I forgot. Because we're returning a string, we're not printing it directly. We have a Ford Mustang. Okay, let's display the horsepower. There's one additional step. We are accessing self, this car that we're creating, but now we need the engine. Let's access the engine attribute. And now, with our engine, Our engine has an attribute of horsepower. We'll use the attribute accessor, that dot, horsepower. 500. I'll add HP, meaning horsepower. Alright, now for the wheels. I'll add another placeholder, access self, access our wheels. Now, our wheels, it's a list. I don't need all 4 wheels. I just need one. If I was to take my list, then access the size, this is what it'll give me. List object has no attribute size. So we need to access one of the elements of our list of wheels. Let's just say the first. Wheels at index 0. Then give me the size. 18. And that's going to be inches. Alright, then let's create a second car object before we finish. We have car 1, car 2 equals car. We need a make, model, horsepower for the engine, and wheel size for the wheels. I will pick a Chevrolet Corvette, and I'm just going to make up some numbers. The horsepower is 670, and the wheel size is 19. Let's display car 2. Car 2, call the display car method. We have a Chevy Corvette with horsepower of 670. The wheel size is 19 inches. So our car class, it owns some objects. It owns an engine, and it owns 4 wheels. That's why composition is different from aggregation. If I were to delete these 2 cars, this engine and the 4 wheels would stop existing. Whereas in our library example in the last video, if I was to delete the library object, the books would still exist. Alright everybody, so that's composition. It's where a composed object, our car, directly owns its components. Our car owns an engine, and it owns 4 wheels. We're creating them within the class. And well everybody, that's composition in Python. Hey, what's going on everybody? So in today's video I gotta talk about nested classes in Python. A nested class is a class defined inside of another class. This has a few benefits. We can logically group classes that are closely related. We can encapsulate private details that aren't relevant outside of the outer class. And also, it helps keep our namespace clean. It reduces the possibility of naming conflicts. So for example, let's say we have 2 classes both named employee. Within this class, I'm just going to print something. This is the first class. Then let's copy our employee class, paste it again. This is the second class. We have a naming conflict. We have 2 classes with the same name. If I were to run this program, we will execute both. This is the first class, this is the second class. It is fairly noticeable that we have 2 classes with the same name, but with Python, we do a lot of importing and exporting of large files. We may not realize there's a name conflict. One concept that'll help us avoid naming conflicts is the use of nested classes. Let's say we have employees for a company and another set of employees for a nonprofit organization. I could write something like this. We'll create a class of company. Within this class of company, we will have an inner class of employee. With our second employee class, we will create an outer class of nonprofit. This is perfectly fine. We can have 2 classes with the same name, as long as they're within different scopes. These 2 employee classes might have different attributes, depending on who they work for. If they work for a company, they might have one set of attributes. If they work for a nonprofit, they might have a different set of attributes. So by using nested classes, this helps keep the namespace clean. We can reuse this employee class because they have different scopes. Now what we're going to do in this example, is create some employee objects that belong to a company object. As a placeholder for now, I'll write pass within the employee class. With our class of company, let's define a constructor. Do pay attention to the indentation. We are within the company class, but not the employee class. This constructor is for the company object we're going to create. If we construct a company object, we need a company name, such as the Krusty Krab. I will assign self.company company name equals the company name that we receive. We are also going to declare an attribute of employees. This attribute will be an empty list. We will append employee objects to our list of employees. Then we will create a method to add employee. We will need a name, meaning name of the employee, and a position. What's their job? For now, I'll write pass. We'll get back to this later. And I will define a method of list employees. And again, I'll write pass. Okay, let's be sure that our company name works. I'm going to create a company object, company equals company, but I have to pass in a company name. I will pick the Krusty Krab. Then, just to be sure that this works, I will display our company's company name attribute. That would give me the Krusty Krab. So we know that that works. Within our employee class, let's define a constructor. Define init. We need a name and a position. Self.name equals name. Self.position equals position. Let's create one more method of define get details. We will return the details of an employee. All we're going to do is return an F string, add two placeholders. We will return self.name and self.position. All right, now within our add employee method, we will construct a new employee object equals. Now, if we're going to access this inner class of employee, we're going to prefix self. Self meaning this company object that we're currently working with. We need the class of employee, then we'll call the constructor. But we have to pass in a name and a position. When we receive a name and a position, we will pass that to the employee constructor. Once we have our new employee object, we're going to take our list of employees, self.employees, use the append method of lists, then add our object of new employee to this empty list. Let's create a few employee objects. We'll take our company, use the add employee method that we have created. We need a name and a position. I will pick Eugene for Eugene Krabs. His position is that he is the manager. Let's create two more. Take our company object, use the add employee method that we have defined. I will pass in a name of this employee as SpongeBob. His position is that he is a cook. Then we have Squidward. Company.add employee method. First name, Squidward. His position is that he is a cashier. So this should run with no problems. Now, I would like to list all of the employees at this company. We'll need to rely on this getDetails method. So when we list our employees, we will return a list comprehension for every employee in self.employees. This is an attribute. It's a list of employee objects. It is iterable. Take each employee that we're iterating through, call the getDetails method, and return it. Now, if I was to take my company, then call the listEmployees method. Whoops, I forgot to print it. We will print each employee's name and their position. However, I think this would look better if we were to use a for loop. For every employee in, take our company, call the listEmployees method. During each iteration, we will print each employee. We have Eugene, that's Mr. Krabs, the manager, SpongeBob the cook, and Squidward the cashier. To demonstrate the reusability of classes, let's create a second company object that has its own employees. Let's rename company as company 1. Then we will create company 2. Company 2 equals, call the company constructor. My second company will be the chum bucket. We'll take company 2, then add 2 employees. Company 2 dot add employee. We will pick Sheldon. Sheldon is the manager. Company 2 dot add employee. Karen will be the assistant. For every employee in company 2, list the employees. During each iteration, print the current employee. We have Sheldon, that's Plankton's first name, he's the manager, and Karen is his assistant. Alright everybody, so those are nested classes. It's a class defined inside of another class. You have an inner class and an outer class. A few of the benefits is that we can logically group classes that are closely related, such as having employee objects within a company object. We can encapsulate private details that aren't relevant outside of the other class. We may have no need to create employee objects outside of this class, and by using nested classes, it helps keep the namespace clean. It reduces the possibility of naming conflicts. With another type of organization, we could create another inner employee class. And well everybody, those are nested classes in Python. Hey, what's going on everybody? Today I'm going to talk about static methods in Python. A static method is a method that belongs to a class rather than any object from that class, any instance. Instance methods, we're already familiar with them. They are methods that belong to individual objects created from that class. They're best for operations on instances of that class, any objects. Whereas static methods, they're best for utility functions within a class that do not need access to class data. I'll demonstrate the differences between an instance method and a static method. We'll begin by creating a class of employee. We'll need a constructor. Let's define that. To create an employee object, we'll need a name and a job position. We will assign self.name equals name, self.position equals position. We will create an instance method of getInfo. We will return employee info. We will return an f-string where we will display self.name equals self.position. GetInfo is an instance method. Each object that we create from this class will have their own getInfo method to return the information on that object, the object's name, and the object's position. Now we'll create a static method. To create a static method, we need a decorator of static method. Static methods are best for general utility functions within a class. We'll define a method to check to see if a job, a position, is valid, which we will name isValidPosition. So static methods, they don't have self as the first argument. We're not working with any objects created from this class. To check to see if a position is valid, we will pass in a job position, which I will name as position. I will create a list of valid positions. Let's assume that our company is the Krusty Krab. What are some valid positions? A manager is a valid position, a cashier, a cook, then let's say a janitor. Then we will return, we'll use a membership operator. Check if position that we receive is in our list of valid positions. What we have done is that we have created a static method. we don't need to rely on any objects to use this method. For example, to use a static method, we will use the name of the class, rather than any object that we create from this class, such as this. We don't need to do that. We type the class name, followed by the static method, isValidPosition. Then I did set this up to accept one argument. Let's check to see if a cook is a valid position. Then I do need to print this. What is the output? A cook is a valid position. What about a rocket scientist? That would probably be Sandy's job. That is false. A rocket scientist is not a valid position at the Krusty Krab. This is a static method. It belongs to the class, not any object created from that class. Now let's create a few employee objects. Let's say employee1 equals a new employee. We have to pass in a name and a job. Eugene will be the first name. That's Mr. Krabs. He will be a manager. Employee2 equals employee. Squidward will be a cashier. Employee3 equals employee. Employee3 will be SpongeBob. SpongeBob will be a cook. To call an instance method, we have to access one of the instances of the class in order to use it. If I want to check the info on employee1, I will access that object, that instance, use the getInfo method, then I need to print it. Take employee1, get the info. Eugene is the manager. Let's do this with employee2 and employee3. Eugene, Mr. Krabs, is the manager. Squidward is the cashier. SpongeBob is the cook. For an instance method, you access an object, then call the instance method. With a static method, you only need to access that class. You don't even need to create any objects from that class. It's a general utility method. Alright everybody, those are static methods. They're a method that belongs to a class, rather than any objects created from that class. They're usually used for general utility functions that do not need access to class data. And well everybody, those are static methods in Python. Hey, what's going on people? So today I gotta talk about class methods in Python. A class method allows operations related to the class itself. They take CLS as the first parameter, whereas instance methods will take self. Self refers to any object created from that class. CLS, meaning class, refers to the class, not any objects. Here's an example. We will create a class of student. We'll need a constructor to construct some student objects. All students will have a name and a GPA. Self.name equals name. Self.gpa equals GPA. We will also create a class variable for this demonstration of count. We will count how many students we create. Whenever we construct a student object, we will access the class of student, take our count variable, increment it by 1. Whenever we create a student object, increase count by 1. I will create an instance method of getInfo. Instance methods have self as the first parameter. We're referring to the object we're currently working with. I will return an f-string where we will display the student's name and their GPA. Self.name, self.gpa. I'll add a comment that this is an instance method. Now to create a class method, to work with class data, we will declare a class method with a class method decorator. Class method. What we're going to do is define a method to get the count, the class variable of count. this method will be called getCount. Rather than self as the first parameter, we'll be working with a class, CLS, meaning class. I will return an f string, total number of students, add a placeholder, CLS count. Let's test this. To call a class method, you take the name of the class, followed by the class method, getCount. And then we do need to print this. What is the count of my current students? Total number of students is 0. Let's create a few student objects. We will create student1 equals, call the student constructor. We have to pass in a name and a GPA. Let's say that the name is SpongeBob. SpongeBob has a GPA of 3.2. We'll create 2 more students. Student 2, student 3. Student 2 will be Patrick. Patrick has a 2.0. Then Sandy. Sandy Smart. In fact, she's a genius. She has a perfect 4.0. Now let's count the number of students. Total number of students is 3. When we call this class method, we can access or modify class data, this class variable of count. Rather than using self, we use CLS for the class. Let's create one more class method. This time I'll calculate the total GPA of all my students. We'll need a class variable to hold that data. Let's say total GPA equals 0. Whenever we construct a student object, we will access our class of student, get the total GPA, then add plus equals this student's GPA that we have just created. Basically speaking, the total GPA, this variable, is going to accumulate all of the GPA of every student and store it as a sum. To find the average, we're going to divide it by the count, the number of students. We'll do that within a class method. To create a class method again, we need to use the class method decorator. I will define a method of getAverage GPA. The first parameter is CLS for class. I will check if CLS count, the count variable of my class, is equal to 0. That means if we have no students. If that's the case, if there's no students, we're going to return 0. Because otherwise we're going to divide by 0 and we'll get an error. Else we're going to return an f string. Follow this formula. We're going to take the total GPA of my class, class.totalGPA, divided by class.count, the number of students we have. That's how to calculate the average GPA. After getting the count of the number of students, to access a class method, we take the name of the class, student, call the class method, getAverageGPA. Then I will print it. Total number of students is 3. The average GPA is 3.06 repeating. After calculating the average, I'm going to add a format specifier of 0.2f, just around to 2 decimal places. And I'll add average GPA : space, then we'll calculate the average. All right, everybody, those are class methods. Instance methods are best for operations on instances of the class, any objects. Static methods are best for general utility functions, which do not need access to class data. Class methods are best used when we're working with class-level data or we require access to the class itself, such as when we're working with class variables. Rather than using self as the first parameter, we're going to use CLS, meaning class. And well, everybody, those are class methods in Python. Yo, what's going on, people? So today I'm going to explain magic methods in Python. Magic methods are also known as dunder methods, meaning double underscore. You typically find these within classes. We're already familiar with one of them, our dunder init method. We have double underscores on the left and double underscores on the right. But there are others. I'll cover a few of the more beginner-friendly ones. So what these methods do is that they're automatically called by using some of Python's built-in operations, such as printing an object, seeing if two objects are equal, greater than or less than. When we use many of Python's built-in operations with objects, we can define and customize the behavior of those objects. So in this demonstration, I'm going to create a class of book. We will construct some book objects. We will define a magic method, a dunder method, of init to initialize these objects. For a book, we need a title, an author, and the number of pages. We'll say num pages. Self.title equals title. Self.author equals author. Self.number of pages equals number of pages. When we call the class of book, we are automatically calling dunder init. So let's create a book object. Book1 equals book. We need a title, an author, and number of pages. So since we're dealing with this topic of magic methods, I'll pick some fantasy-related books. For my first book, I'll pick The Hobbit. That's the title. The author is J.R.R. Tolkien. The number of pages is 310. So for my next book, book 2, I will pick Harry Potter and the Philosopher's Stone. The author is J.K. Rowling. The number of pages is 223. Then we have book 3. For my third book, I will pick The Lion, The Witch, and The Wardrobe. The author is C.S. Lewis. The number of pages is 172. Okay, here are my 3 book objects. When we call the class of book and pass in arguments, we will call the dunder init method. It's a magic method. It's automatically called behind the scenes. Within this magic method, we can define and customize the behavior of objects. And in this example, we're just assigning the attributes of title, author, and number of pages. That is one built-in operation of Python. What would happen if I was to print book 1 directly to the console? Here's what happens. Well, we're given a memory address. Here's book 2 and book 3. Well, we can customize this behavior. We will use the dunder string method. Double underscore, str meaning string, double underscore again. We have one parameter of self. Instead of returning a memory address, we can customize this behavior. Let's instead return an f string. I'll add 2 placeholders. We will display self.title, the title of the book, by self.author. And I'll place the title within single quotes. Now let's print book 1. We have The Hobbit by J.R.R. Tolkien. Let's print book 2. Harry Potter and the Philosopher's Stone by J.K. Rowling. And book 3. The Lion, the Witch, and the Wardrobe by C.S. Lewis. So that is dunder string. We can return a string representation of the object when we print it directly to the console. Here's another dunder method. We can check to see if 2 objects are equal. I will print is book 1 equal to book 2. That gives me false. If they were to have the same title, the same author, and the same number of pages, then Python would say they're not equal still. So let's customize this behavior. We will define a method of dunder equals, which is just eq. For parameters, we have self, the first book we're examining, in this case book 1, and other. Other means the other book. We're examining 2 objects for equality. To do that, we'll see if the title of two books and the author is the same. We'll disregard the number of pages. You can have two different versions of the same book. They might have different font sizes, or the dimensions of the physical pages might be different. So we will return a Boolean value. We will examine if self, that's the first book, is the title attribute equal to our other book's title, and is the author of the first book, self.author, equal to our other book's author. If I were to run this, we get false. Book 1 does not equal book 2, but if they have the same title, I'm going to replace these, and the same author, then they would be equal. And we'll disregard the number of pages. Let's say that with this version of The Hobbit, they're using a smaller font size, so there's less pages. We're using dunder equals to compare if two objects are equal. What if I was to print book 2 is less than book 3? Like, what does that even mean? And I'm just going to get rid of these two lines. Type error, less than is not supported between instances of book and book. So we can't use less than on two objects. But we can customize that behavior by using dunder less than, which is just LT. We're examining one book and the other book. Self and other. Let's compare the number of pages. We'll compare if the pages of book 2 is less than book 3. We will return a Boolean value. Is self.number of pages less than other.number of pages? So now, this should not give us an error. Book 2 does not have less pages than book 3. Another would be greater than. I'll just copy what we have. Dunder GT for greater than. For our first book of self, is it greater than the number of pages of the other book? Well, that's true. The number of pages of book 2 is greater than book 3. Let's use dunder add to add the pages of two books together. What would happen if I were to add two books together? Book 2 plus book 3. Well, we get a type error. Unsupported operand for book and book. Well, to customize the behavior of addition, we will define dunder add. We have self and other for the other object. Let's add the pages together of two books. Maybe we need a summer reading list and we would like to see what the total number of pages is. I will return self.number of pages attribute plus our other book's number of pages. That would give me 395. That's 223 plus 172. Heck, I'll even put this within an F string. 'Cause why not? Then I will add the word pages. 395 pages. Within an object, we can search for a keyword within one of the attributes. So let's find the word lion within book 3. To do that, I would write a statement like this. Lion in book 3. Type error. Argument of type book is not iterable. We will define dunder contains. Besides self, we will pass in a keyword that we're searching for. I will return, then we'll use the in membership operator, is our keyword in self.title. I'm looking for the word lion. That's going to return true if lion is in the title of this book. Or is our keyword in self.author. Maybe we're searching for an author. Let's try that again. That returns true. Lion is in book 3. However, lion is not within book 1. That's false. Is rolling in book 2. That's the author. That is true. Is rolling in book 3. That is false. That is dunder contains. We are searching for a keyword in an object. Now, we could search for a key given an object. For book 1, we'll use the index operator and look up an attribute. Let's get the title of book 1. The default behavior is that we get a type error. Book object is not subscriptable. So to customize this behavior, we will use dunder get item. Besides self, we have one parameter of key. We're accessing book attributes by indexing. With this object, return the value at this key. What's that attribute? We will check if our key that we receive is equal to title, which it is in this case. We will return self.title. What's the title of the book? So that would give me The Hobbit. Here's book 2 and book 3. What if the key is author? None. We didn't set that up yet. If key is equal to author, then return self.author. The author of book 3 is C.S. Lewis. 2 is J.K. Rowling. Book 1 is J.R.R. Tolkien. What about number of pages? Num pages. Well, we're not set up for that yet. I'm going to turn this into an else if statement. Else if key is equal to num pages, then we will return self.num pages. The number of pages in book 1 is 310. Book 2 is 223. Book 3 is 172. What if there is no key? Otherwise, if there is no matching key, I'll add an else statement. Let's return an f string key placeholder. Our key that we pass in as an argument was not found. What do books not have? Well, they don't have audio, I guess, unless it's an audio book. Is there a key of audio in book 3? There is not. Key audio was not found. And I'll place that within single quotes. Much better. Alright, everybody, so those are magic methods, also known as dunder methods, meaning double underscore. They are automatically called by many of Python's built-in operations. They allow developers to define or customize the behavior of objects when we use those built-in operations. And well, everybody, those are magic methods in Python. Hey everybody, so in today's video I got to talk about the property decorator in Python. The property decorator allows us to define a method as a property. We can access it like it's an attribute. One of the benefits is that when reading, writing, or deleting attributes, we can add additional logic. The property decorator gives us a getter method to read, a setter method to write, and a deleter method to delete when working with attributes. In this example, we'll create a class of rectangle. We need a constructor. Let's define that. When constructing a rectangle object, we will need a width and a height. We will assign the attribute of width equal to the width that we receive when constructing this object. Self.height equals height. Let's construct a rectangle object. Rectangle equals rectangle. We need to pass in a width and a height. Then I will print my rectangle's width, rectangle.width, and the height, rectangle.height. With my rectangle, the width is 3, the height is 4. Using the property decorator, when reading these attributes of width or height, I can write some additional logic. Let's say that when accessing the width or the height, I would like to display one digit after the decimal, then add centimeters. Here's one way in which I can do that. For each of these attributes, I'm going to create a method. We will define a method of width, no parameters besides self, For now, I'll write pass and define height. Preceding each of these methods, I will use the property decorator. So at property. Now, when accessing the width or the height, will be returned with whatever's within these methods of width and height. But there's one change we're going to make to these attributes. We'll set these attributes to be private. Prefix each of these attributes with an underscore. This tells you and other developers that these attributes, they're meant to be protected. They're internal. We shouldn't access the width or the height directly outside of this class. Technically, we could. I will access the internal version of width and height. We get 3 and 4, but we do have a warning. Access to a protected member width of a class. That applies to height as well. Our width and our height are only meant to be used inside of this class. If we need to get the width and the height, we will do so through these getter methods, provided by the property decorator. So when accessing the width, let's return an f string. I will access self.private width, add a format specifier to display one digit after the decimal, 0.1f, followed by centimeters. We'll do this with the height as well. We will return self.private height. So now when we access the width or the height, we will do so using these getter methods. If I access these private width and height attributes instead, again, they will be 3 and 4. It's kind of like they're raw. These attributes are meant to be used internally, inside of the class. So that's the point of a getter method. We can add additional logic when reading one of these attributes when we try to get them. We can also add setter methods if we would like to set or write these attributes. Here's how. Let's take our width. We will create a decorator of @width.setter. When attempting to set the width, we will do so using this method. We will define our method name of width. We will have one parameter, a new width. We don't want the parameter name to be the same as the method name. That's why we're naming it something different. When setting the width, let's check to see if the new width is greater than 0. If so, we will take self.private width equals our new width. Else, let's print something. Let's print width must be greater than 0. And let's do this with the height. Height.setter, define height. Pass in a new height. If our new height is greater than 0, assign self.private height equals the new height. Else print height must be greater than 0. Before printing the width and the height, let's take our rectangle's width, set it to be 0, then see what happens. Well, we get that message. Width must be greater than 0. If I were to set width to be 5, well, that does work. Our width is now 5. Let's change the height. Rectangle.height. I will set this to be -1. Height must be greater than 0, and the height hasn't changed. What about 6? 6 does work. When using these setter methods, we can add additional logic when writing or changing one of these attributes. These are setter methods. Now, if you need to delete an attribute, here's how. There is a delete keyword. We will delete our rectangle's width and delete our rectangle's height. In this series, we really won't be using the delete keyword, but you should still know that it exists. So we will create a deleter method. Take one of the attributes, in this example width, we will create a deleter method. The method name will be width, the name of the attribute. There will be no parameters besides self. We will delete self.private width. Then let's print something just to confirm that this was deleted. Width has been deleted. Same thing applies to height. Take the attribute of height, define height. Delete private height. Height has been deleted. When deleting our width or our height, we get that confirmation message. Width has been deleted and height has been deleted. All right, everybody, so that is the property decorator. We can define a method as a property, meaning it can be accessed as if it was an attribute. One of the benefits is that we can add additional logic when we read, write, or delete attributes. The property decorator gives us a getter, setter, and deleter method. Getter methods to read, setter methods to write, and deleter methods to delete. And well, everybody, that is the property decorator in Python.